The balanced weight is one of the widely used methods for imbalanced classification models. Unlike the oversampling and undersampling methods, the balanced weights methods do not modify the minority and majority class ratio. Instead, it penalizes the wrong predictions on the minority class by giving more weight to the loss function. In this tutorial, we will compare logistic regression and random forest models, and how balanced weight impacts the model performance for the imbalanced classification. We will cover baseline random forest model, baseline logistic regression model, balanced weight for random forest model, balanced subsample weight for random forest model, and balanced weight for a logistic regression model. Which model do you think has the best performance? Let's check it out. Hi everyone, welcome to Grab and Go Info. We publish step-by-step machine learning tutorials every week. If you are interested in data science, machine learning, deep learning, and natural language processing, please subscribe to the channel. Let's get started. The first step is to import libraries. We need to import make classification from sklearn to create the modeling dataset. Import pandas and numpy for data processing. Counter will help us count the number of records after oversampling and undersampling. Matplotlib and Seaborn are for visualization. We also need the train test split to create training and testing dataset. Cross-validate and stratified k-fold are for k-fold cross-validation. Random forest classifier and logistic regression are for modeling. Class weight is for adjusting weights. And classification report is for model performance evaluation, using make classification from the sklearn library. In the second step, we create an imbalanced dataset with two classes. The minority class is 0.5% of the dataset. I made two features to predict which type each data point belongs to. The dataset gives us around 1% data points for the minority class. It is higher than the specified weights of 0.5% but works for demonstrating the rare event modeling process. Let's visualize the data using a scatter plot. We can see that the majority of the dataset belongs to class 0, and a small portion of the dataset belongs to class 1. The third step is to do a train test split for the imbalanced data. In this step, we split the dataset into 80% training data and 20% validation data. Random state ensures that we have the same train test split every time. The seed number for random state does not have to be 42, and it can be any number. The train test split gives us 80,000 records for the training dataset and 20,000 for the validation dataset. Thus, we have 79,183 data points from the majority class and 817 from the minority class in the training dataset. In step 4, we will check the model performance using the imbalanced dataset directly. A model without oversampling or undersampling gives us a baseline to compare the model performance. A random forest model is used as an example here. We use cross-validation to evaluate the model performance and use minority class recall as the North Star metric. The stratified 5-fold cross-validation gives the recall value of 0.043 and the standard deviation of 0.016. This shows that the model only captured 4% of the minority class. In step 5, we will talk about the algorithm behind the balanced weights. The weights are calculated using the inverse proportion of class frequencies. There are 79,183 data points from the majority class and 817 from the minority class in our training dataset. So the weight for the majority class would be 1.010. And the weight for the minority class is 97.919. Sklearn has a built-in utility function compute class weight to calculate the class weights. If we multiply the compute class weight by 2, the results are the same as our manual calculation. In step 6, we apply balanced class weight to the random forest model. The random forest classifier in Sklearn has the option of class weight. The default value for class weight is none, meaning that all classes have the same weight of 1. Class weight can take two values, balanced and balanced subsample. We will use balanced for this step and balanced subsample for the next step. The class weight equals balanced option did not increase the model performance. On the contrary, it performed worse than the baseline model. Thus, we can see that it's crucial to have a baseline model to compare with, and do not blindly choose an imbalance adjustment algorithm and assume it has been taken good care of. In step 7, let's try class weight equals balanced subsample and see how it performs. The difference between balanced subsample and balanced is that balanced subsample calculates the weights based on the samples for each tree, while balanced has the same weights for every tree based on the calculation of all the modeling data points. We got the same results as the class weight equals balanced option. Balanced weights did not improve the performance of a random forest. Is it because of the modeling algorithm we chose? Let's try the balanced weights on the good old logistic regression and see if it improves the model performance. In step 8, we use balanced weights for logistic regression. We can see that running the logistic regression on the imbalanced dataset gave us a recall of 0, meaning that none of the minority class data points was predicted correctly. Thus, the logistic regression baseline model has worse performance than the random forest baseline model. Now let's try adding the balanced weights by setting class weight equals balanced. What a big difference the balanced weights made. The 5-fold stratified cross-validation improved the recall from 0 to 57.5%. The comparison above shows that the logistic regression with balanced weights has the best model performance. Now let's train the model using all the training dataset. Logistic regression gets a 55% recall value on the minority class, which significantly improves the baseline and balanced weights random forest models. In this tutorial, we compared how balanced weight impacts the logistic and random forest models for imbalanced datasets. We compared random forest, logistic regression, random forest with balanced weight, and logistic regression with balanced weight. If you found the information in this tutorial helpful, please click the like button and subscribe to the channel. If you prefer the written version of the tutorial, please go to grabandgoinfo.com. I will put the link in the video description. This is the blog post for this tutorial. It has all the code and explanations in the YouTube video. If you are interested in learning about the oversampling and undersampling methods, please refer to my videos for oversampling and undersampling methods for imbalanced classification using Python, and ensemble oversampling and undersampling for imbalanced classification using Python. Thank you for watching. See you in the next video.